So we were trying to create the matrix that represents this linear orthogonal symmetry. So we have created those two. We have those two bases, which are orthonormal bases of F and F orthogonal. And the good thing is that if you concatenate them, you have a basis of your whole space E. Okay, so if we're trying to make the matrix in that orthonormal basis of that symmetry, what's the image of E1? It's going to be E1 because it's F, so anything that belongs to F is going to be sent to itself. Okay, so basically you're going to have, if that goes up to S of EP, you're going to have a block here that corresponds to the identity. Okay, because each vector is going to be sent to itself, right? And of course, 0 times the vectors from the orthogonal. Okay, so here you've got an identity block, right? And sorry, and what's happening for the other vectors? The one from EP plus 1, S of EP plus 1 up to n, they all belong to F orthogonal, so they are going to be sent to their own opposite. Okay, S of EP plus 1 is going to be minus EP plus 1. S of En is going to be minus En. So here we've got a block that corresponds to negative identity matrix. So -1, -1, etc., -1, and zeros everywhere, and of course 0 above. All right. So, and obviously, what kind of matrix is that? That's an orthogonal matrix because, well, the if you consider the columns, they are very trivially create their own orthonormal basis. So that's just going to so we're using this result that a matrix is orthogonal if and only if its matrix in an orthogonal basis, orthonormal basis. Well, that's one point, is symmetric. That's one thing. And also that an orthonormal matrix corresponds to, for instance, the rows or the columns make an orthonormal family. Okay, so this being said, let's have a closer look at what the orthogonal symmetries in R2 and R3 are going to be. Okay, so in R2, basically you have three choices depending on what kind of space you choose for F. So we are in dimension 2. Either F is just 0, that case. So in that case, if F is just 0, well, F orthogonal, so that's F, that's just the 0 element. That's barely a linear space, but then its orthogonal is going to be actually the whole R2 space. Okay, and so, but you can really write that anything in R2 can be written as an element that belongs to F. It's just 0 plus some x2, where x2 belongs to F orthogonal, which happens to be R2. And so that if you apply S of x, you get minus x, okay, because x is equal actually to its x2 part. That's enough. All right, so that the matrix is going to be minus identity. All right. And so it says corresponds to a rotation of angle pi. Well, obviously, if you take the opposite of it's going to be, well, angle pi in a positive direction. That's going to be sent here. All right. Okay, so not very interesting. Another not very interesting case is when you choose F itself to be R2. Okay, so in that case, F is R2, and so it's just X only has that X1 part, so that and the F orthogonal is just the 0 element, and so that's 0, and so that S of X is equal to X. And so the representing matrix is going to be the identity. Okay, all right, so these were not very interesting, but more interesting, we have that second case where F has dimension 1. So let's assume we have one direction, F, Okay, it goes through 0, otherwise it wouldn't be a linear space. It has its orthogonal. So that the 0, so the 0 is here, and that's going to be F orthogonal. And I can absolutely give you an orthonormal basis of ortho by choosing one unit vector along F and one unit vector along F orthogonal. Okay, these two vectors. These two vectors create a basis of R2. So any x that belongs to R2 can be very directly described as one part x1 here, one part x2 here. Both are the orthogonal projections on F and F orthogonal, and you know now very well orthogonal projections. And so that S of x is going to be, we keep the x1, we take the opposite of the x2, that's going to be S of x. All right, if I take these steps. But anyway, if we are looking for the matrix representing this symmetry, so if I take my basis, this one, E1 and E2, E1 is a direction vector of F, and E2 is, well, is going to be a unit vector orthogonal to it, and so it's going to be a direction vector of F orthogonal. So we have that S of E1 is going to be itself, so E1, 1, 0, so in that basis E1, E2, and S of E2 is of course going to be sent to its opposite, negative E2. Okay, so that the matrix is going to be represented by 0 times E1 plus negative 1 times E2, all right? So that's fairly nice. And as an example, if I give you a matrix, two matrix, let's say this one, 1 over 5, 3, 4, 4, negative 3. Oh, I guess there's something I haven't finished in the previous theorem. So let's go back. Sorry about to the previous theorem. We said, okay, let's do this one. Okay, so we have already talked about that. An orthogonal symmetry is a linear isometry, and we could find its representing basis, and we get a bit further by saying a symmetry is orthogonal if and only if its matrix in an orthogonal basis is symmetric. So assuming you have a symmetry, so you know that you have m square is equal to the identity, and so that m minus 1 is equal to m. Then, of course, you get that if it's orthogonal, the other property of orthogonal matrices is that m minus 1 is equal to the to its transposed. So, but m minus 1 is equal to m transposed as m is orthogonal. So according to what we have at the same time that m is equal to its inverse because it's a symmetry, and m is its inverse is equal to its sorry, that's a transpose sign, and that's the inverse is equal to its transpose. So from that we get that m is equal to its transpose, and so that the matrix is symmetric. Okay, so let's go back to our example. How can we use these kind of things, these kind of results? So given this matrix M, first it's symmetric. Then you check that M squared is equal to the identity. From that, what can you deduce? You can deduce that of course, you have to compute the m square. From this, you can deduce that M is an orthogonal symmetry. If I can write, M is an orthogonal symmetry. Okay, that's one thing. And then how do you find the axis of the symmetry, so the F, and of course the F orthogonal is going to be set. So the axis of the symmetry, you compute the kernel just as you did before with any symmetry. So you compute the kernel of M minus the identity, and that's going to be the F space. And you should try to do that. And so maybe pause and compute that kernel and check that you're going to find the following result. So assuming you have paused, you should find the spanning vector of f, which is equal to, for instance, 2, 1, one of the spanning vectors. So that's not normalized. You can always normalize it by a nice square root of 5. And you can also, from that, you don't even have to compute the kernel of M plus identity to find the direction vector of F orthogonal. You just have to find an orthogonal vector to the previous one. So for instance, -1, 2. All right, so for instance, maybe pause and find the span. Okay, so you could get anything that is orthogonal to the previous one. So for instance, -1, 2 is going to be orthogonal to the previous one. All right, so that's how you work in R2. What's now happening in R3? Well, you've again have all these different cases. So trivial cases, non-interesting ones. When the dimension of f is 0, you get the opposite of the identity. Other trivial case, when f has dimension 3, you get exactly the identity. And the two interesting cases are those ones. So first case, f is dimension 1, so that's it's orthogonal. F orthogonal has dimension 2, so assuming you've got some orthogonality between those two directions. All right, and again, if you choose the right basis, so you take one unit vector in F and two unique orthogonal vectors in, so assuming you've got, so that's some kind of perspective for F orthogonal. So you take E1, E2, E3, and we said you should understand that you get this kind of matrix. Anything that has direction E1 belonging to F is going to be sent to itself. So it's going to have S of E1 is going to be 1 times E1 and 0 times E2, 0 times E3. And E2, anything that belongs to the space F orthogonal is going to be sent to its opposite. So S of E2 is negative E2, F of E3 is negative E3. So you get these spaces, this matrix. And absolutely similarly, the third case where F has dimension 2 and F orthogonal has then dimension 1. Okay, and again, you make the right choice of basis. So you take an orthonormal basis in F, E1, E2, and you take one vector in F orthogonal, so that's F orthogonal, and of course you get this kind of representation. And next, we are going to identify in general isometries in R2 and R3. And so that's going to be for the next videos or even class. Thank you.